Welcome to this comprehensive video on the cosecant identity. Today we'll explore one of the most important reciprocal trigonometric functions and discover how it simplifies complex mathematical problems. The cosecant function, abbreviated as CSC, is simply the reciprocal of the sine function. This means that cosecant of x equals 1 divided by sine of x. This reciprocal relationship is fundamental because it allows us to solve problems where sine appears in the denominator, and it connects all the trigonometric functions in a beautiful mathematical framework. Throughout this video, we'll build your understanding step by step. We'll explore how cosecant appears on the unit circle, examine its mathematical properties, discover real-world applications, and work through detailed examples to solidify your knowledge. By the end of this video, you'll have a complete understanding of the cosecant function and be able to apply it confidently in your mathematical work. Are you ready to master the cosecant function? Now we'll define cosecant more formally. Cosecant is fundamentally the reciprocal of the sine function, which means we flip the ratio that defines sine. Let's start with a right triangle. We have our angle x, and we need to identify the three sides: the hypotenuse, the side opposite to angle x, and the adjacent side. The hypotenuse is the longest side opposite the right angle. The opposite side is across from our angle x. The adjacent side is next to our angle x. First, let's recall how sine is defined. Sine of angle x equals the opposite side divided by the hypotenuse. This gives us a ratio that describes the relationship between these two sides. In sine, we take the opposite side and divide it by the hypotenuse. The green line represents the opposite side, and the red line represents the hypotenuse. Now, cosecant is defined as the reciprocal of sine. Instead of opposite over hypotenuse, cosecant is hypotenuse over opposite. We literally flip the fraction. This reciprocal relationship means that cosecant equals 1 divided by sine. When we flip a fraction, we're finding its reciprocal, which is exactly what cosecant represents. Think of it this way. If sine uses opposite over hypotenuse, then cosecant simply flips this ratio to use hypotenuse over opposite. The sides switch positions in the fraction. Let's summarize this key concept. Cosecant is the reciprocal of sine, which means we take the hypotenuse and divide it by the opposite side. Understanding this reciprocal relationship is crucial because it shows us that cosecant and sine are intimately connected. Wherever sine is large, cosecant will be small, and wherever sine is small, cosecant will be large. This reciprocal relationship forms the foundation for understanding all the properties and applications of the cosecant function that we'll explore next. Now we'll explore how the cosecant function appears on the unit circle. The unit circle is a powerful tool that helps us visualize trigonometric functions geometrically. Let's place a point P on the unit circle. We'll draw a radius from the center O to point P and drop a perpendicular line from P to the x-axis, meeting it at point Q. The cosecant of angle x is defined as the ratio of the length OP to the length PQ. Since OP is the radius of our unit circle, it equals 1. And PQ represents the y-coordinate of point P. Since the radius of the unit circle is always 1, this simplifies to cosecant of x equals 1 divided by the y-coordinate of point P. For our current point at 30 degrees, the y-coordinate is 0.5, so cosecant of 30 degrees equals 1 divided by 0.5, which equals 2. Watch what happens to the cosecant value as we move point P around the unit circle. Notice how the cosecant changes as the y-coordinate changes. At 90 degrees, the y-coordinate equals 1, so cosecant of 90 degrees equals 1 divided by 1, which is 1. This is the minimum positive value of cosecant. Now watch what happens as we approach 180 degrees, where the sine function equals 0. When the y-coordinate approaches 0, as it does at 0, 180, and 360 degrees, the cosecant becomes undefined because we cannot divide by 0. The unit circle shows us that cosecant is simply the reciprocal of the y-coordinate. This geometric interpretation helps us understand why cosecant has the values it does and why it's undefined at certain angles. Now we need to understand three crucial properties of the cosecant function: its domain, range, and periodicity. These properties determine where the function exists, what values it can take, and how it repeats. The domain of the cosecant function is determined by where it's defined. Since cosecant equals 1 divided by sine, we need to find where the denominator equals 0. The sine function equals 0 at integer multiples of pi. This means x equals n times pi, where n is any integer, negative 2 pi, negative pi, 0, pi, 2 pi, and so on. On the unit circle, sine equals 0 at 0 radians and pi radians. These correspond to the points where the circle intersects the x-axis. Therefore, the domain of cosecant is all real numbers except integer multiples of pi, where the function has vertical asymptotes. To find the range of cosecant, we start with the range of sine. The sine function produces values between -1 and +1 inclusive. Since cosecant is the reciprocal of sine, we need to consider what happens when we take 1 divided by values between -1 and 1. When sine equals 1, cosecant equals 1. When sine equals -1, cosecant equals -1. But when sine equals 1/2, cosecant equals 2. When sine equals -1/2, cosecant equals -2. As sine approaches 0, cosecant approaches infinity. This means the range of cosecant is all real numbers except the open interval from -1 to 1. The periodicity of cosecant is directly related to the periodicity of sine. The sine function repeats every 2 pi radians. Since cosecant is 1 over sine and sine of x plus 2 pi equals sine of x, then cosecant of x plus 2 pi also equals cosecant of x. This means the cosecant function has the same period as sine, 2 pi radians. The pattern repeats identically every 2 pi units along the x-axis. To summarize the 3 key properties of cosecant, the domain excludes integer multiples of pi where vertical asymptotes occur. The range includes all real numbers except the interval from -1 to 1. The period is 2 pi radians, meaning the function repeats its pattern every 2 pi units. Understanding these properties is essential for graphing the cosecant function and solving trigonometric equations. These characteristics make cosecant unique among the trigonometric functions and determine how it behaves in mathematical applications. Now we'll explore an important property of the cosecant function. It is what mathematicians call an odd function. Understanding this property will help you simplify trigonometric expressions and solve equations more efficiently. An odd function is a function that satisfies a specific symmetry property. Mathematically, a function f is odd if f of -x equals -f of x for all x in the domain. The cosecant function is an odd function, which means cosecant of -x equals negative cosecant of x. This property comes directly from the fact that sine is also an odd function. Let's prove this step by step. First, we use the definition of cosecant. Cosecant of -x equals 1 over sine of -x. Since sine is an odd function, we know that sine of -x equals negative sine of x. So we can substitute this into our expression. We can factor out the negative sign from the denominator, giving us -1 over sine of x. And since 1 over sine of x is the definition of cosecant of x, we get negative cosecant of x. This completes our proof. Now let's visualize this property using the unit circle. We'll see how the cosecant values for positive and negative angles relate to each other. Let's take a specific angle, say 30 degrees or pi over 6 radians. We'll mark this point on the unit circle in yellow. Now let's mark the point for -30 degrees, which is negative pi over 6 radians, shown in red. For our positive angle of pi over 6, the sine value is 1/2, so the cosecant value is 2. For the negative angle of negative pi over 6, the sine value is -1/2, so the cosecant value is -2. Notice that cosecant of negative pi over 6 equals negative cosecant of pi over 6. This demonstrates the odd function property. The odd function property means the cosecant graph has a special symmetry. If we rotate the graph 180 degrees about the origin, we get the same graph back. Here we see portions of the cosecant graph. The yellow segment shows positive values, while the red segment shows the corresponding negative values. This symmetry about the origin is the defining characteristic of odd functions, and it makes the cosecant function very useful in simplifying trigonometric expressions. The odd function property allows us to quickly simplify expressions involving negative angles. For example, cosecant of -45 degrees equals negative cosecant of 45 degrees, which is negative square root of 2. Similarly, cosecant of negative pi over 3 equals negative cosecant of pi over 3, which simplifies to negative 2 square root 3 over 3. The key takeaway is that whenever you encounter cosecant of a negative angle, you can immediately convert it to the negative of cosecant of the positive angle. This property is essential for solving trigonometric equations and simplifying complex expressions. Now we'll explore one of the most important identities involving cosecant, the Pythagorean identity with cosecant. This identity connects cosecant and cotangent in a powerful way. The Pythagorean identity with cosecant states that cotangent squared of a plus 1 equals cosecant squared of a. But where does this identity come from? We start with the fundamental Pythagorean identity, sine squared of a plus cosine squared of a equals 1. This is the foundation from which we'll derive our cosecant identity. To derive the cosecant identity, we divide every term in the fundamental identity by sine squared of a. This is the key transformation step. When we divide each term by sine squared of a, we get sine squared of a over sine squared of a plus cosine squared of a over sine squared of a equals 1 over sine squared of a. Now we simplify each fraction. The first term, sine squared over sine squared, simplifies to 1. The second term becomes cosine over sine, which is cotangent. The right side becomes 1 over sine squared, which is cosecant squared. The first fraction simplifies to 1, since sine squared divided by sine squared equals 1. We can rewrite the second term as cosine of a over sine of a, all squared. The right side becomes 1 over sine of a, all squared. Remember that cosine over sine is the definition of cotangent, and 1 over sine is the definition of cosecant. Substituting our trigonometric identities, we get 1 plus cotangent squared of a equals cosecant squared of a. We can rearrange this to the more common form. Cotangent squared of a plus 1 equals cosecant squared of a. This is exactly the Pythagorean identity with cosecant that we introduced at the beginning. Notice how it connects cotangent and cosecant through this fundamental relationship. This Pythagorean identity with cosecant is a powerful tool in trigonometry. It allows us to simplify complex expressions, solve equations involving cotangent and cosecant, convert between these functions, and verify other trigonometric identities. Remember this key relationship. Cotangent squared plus 1 equals cosecant squared. This identity will be essential as we continue exploring trigonometric functions and their applications. The cosecant function isn't just an abstract mathematical concept. It has numerous practical applications across many fields, from engineering and physics to music and astronomy. Understanding these real-world uses helps us appreciate why trigonometric functions like cosecant are so important in science and technology. In structural engineering, the cosecant function appears in beam deflection calculations. When a load is applied to a beam at an angle, engineers use formulas involving cosecant to determine how much the beam will bend or deflect under that load. In electrical engineering, cosecant appears in AC circuit analysis, particularly when calculating resonance frequencies and impedance. The phase relationships between voltage and current in RLC circuits often involve cosecant functions, especially when dealing with reactive components. Wave analysis is another important application of the cosecant function. In acoustics, electromagnetic theory, and signal processing, cosecant helps describe wave amplitudes, frequencies, and phase relationships. This is crucial for understanding sound waves, radio waves, and light waves. Cosecant also appears in astronomy for calculating stellar distances and orbital mechanics, in quantum physics for wave function analysis, and in music for harmonic analysis and sound synthesis. The common thread is that whenever we need to work with the reciprocal of sine in periodic or oscillatory phenomena, cosecant provides an elegant mathematical tool. These real-world applications demonstrate that cosecant is far more than just an abstract mathematical concept. From the bridges we cross, to the music we hear, from the circuits that power our devices, to the waves that carry our communications, the cosecant function plays a vital role in understanding and designing the world around us. Now that we understand the cosecant function and its properties, it's time to put this knowledge into practice. We'll work through 3 examples that demonstrate how cosecant helps us solve real mathematical problems. Example 1. We have a right triangle where we know one angle is 30 degrees and the side opposite to this angle is 6 units long. We need to find the hypotenuse. Here's our triangle. We can see the 30-degree angle, the opposite side of length 6, and we need to find the hypotenuse h. We start with the definition of cosecant. Cosecant of 30 degrees equals the hypotenuse divided by the opposite side. Substituting our known values, cosecant of 30 degrees equals h divided by 6. To solve for h, we multiply both sides by 6. So h equals 6 times cosecant of 30 degrees. We know that cosecant of 30 degrees equals 2. This is because sine of 30 degrees is 1/2, and cosecant is the reciprocal of sine. Therefore, h equals 6 times 2, which gives us 12 units. The hypotenuse is 12 units long. This demonstrates how cosecant helps us find missing sides in right triangles when we know an angle and its opposite side. Example 2. Now we'll simplify a more complex trigonometric expression involving cosecant. We need to simplify cosecant squared x minus 1, all divided by cosecant x. We start by recognizing a Pythagorean identity. Cosecant squared x minus 1 equals cotangent squared x. This comes from the identity cotangent squared plus 1 equals cosecant squared. Substituting this identity, our expression becomes cotangent squared x divided by cosecant x. Now we use the definitions. Cotangent x equals cosine x over sine x, and cosecant x equals 1 over sine x. Substituting these definitions, we get cosine squared x over sine squared x, all divided by 1 over sine x. When we divide by a fraction, we multiply by its reciprocal. This gives us cosine squared x over sine squared x times sine x over 1, which simplifies to cosine squared x over sine x. Our final simplified expression is cosine squared x over sine x. This shows how cosecant identities help us simplify complex trigonometric expressions. This technique of using trigonometric identities is essential for solving more complex problems in calculus and advanced mathematics. Example 3. Here's a real-world application. A surveyor stands 50 meters away from a building and measures the angle of elevation to the top as 60 degrees. We need to find the building's height. Here's our setup. The building height h is what we're looking for. The horizontal distance is 50 meters, and the angle of elevation is 60 degrees. We could use tangent here, but let's see how cosecant can also solve this problem. First, we note that tangent of 60 degrees equals h over 50. We know that sine of 60 degrees equals square root of 3 over 2. Therefore, cosecant of 60 degrees equals 1 over sine of 60 degrees, which is 2 over square root of 3. In our triangle, cosecant of 60 degrees equals the hypotenuse over the opposite side, which is the square root of h squared plus 50 squared, all over h. Using the simpler approach with tangent, h equals 50 times tangent of 60 degrees, which is 50 times square root of 3, approximately 86.6 meters. This example shows how trigonometric functions, including cosecant, help us solve real-world measurement problems. While tangent was more direct here, understanding cosecant gives us multiple approaches to solve the same problem. These three examples demonstrate the power and versatility of the cosecant function. Whether finding missing triangle sides, simplifying expressions, or solving real-world problems, cosecant is an essential tool in trigonometry. Remember to always check your work and ensure your answers make sense in the context of the problem.